This is the video one about Posicast Control. So this video and the following ones will constitute an education journey about Posicast Control. So first I'm going to do a preface and just saying how this learning story began. I was reading a obituary about the great professor Otto Schmidt, and reading that obituary, everybody knows that about the Schmidt predictor. But besides the Schmidt predictor and other techniques, there was one that I never heard about it. And this is Posicast Control. We can see that in this link, you can see this in this paragraph in a lecture about Posicast Control. And he got an explanation very interesting about the online demonstration that was done about it by Professor Schmidt. And with this, I began to search about information about Posicast Control. So I requested a copy of his book via Internet Library Loans. This was a book from 1955, is this one, Control Systems Engineering. And he got at least one chapter about Posicast Control. Then I also read the paper from 1957, this one, Posicast Control of Damped Oscillatory Systems. This is very interesting as well. So based on these two and then others that I searched, I began my learning process about process control that I will explain to you. So you may now be asking, why should I care to learn about such a whole technique as Posicast Control? That's what you may be thinking. And the answer to that question is this one that I'm going to give you, but this is partial because flexible structures, vibration control, the techniques, the modern techniques are based on, they were originally based on Posicast Control. The power systems electronics got a lot of applications about this type of control. Cane control also has applications, and so we can say that the Posicast control principle led to the development of flexible systems and vibration control theory from the last decades. And if you want to search, there's some. This is one reference that it makes a review of the 50 years of command shaping for flexible systems, and also it got a reference over there, of course, to Posicast control. So what is the problem? The problem is very simple. Consider this suspended load. This is in the initial position, and the problem is how to move the suspended load from the initial position to the final position without having this oscillation in the final position. So if you do this, move this trolley or this car very fast and stop in the final position, of course what you will observe is an oscillation towards the final position. And so this is the question. We would like to move the load from the initial position to the final position without any oscillation in the final position. So assuming that we are going to actuate this car or this trolley, which is suspending, which is holding the load, and we somehow we can measure or estimate the position of the load, the final position. Okay, so assuming now that we are in open loop, so we don't have, in this case, we don't have feedback, no feedback at all. So we got the system here, this trolley with assuming that this trolley is the load. We got the input system here, the input signal, sorry, and the output signal. Okay, so it is obvious that this system can be represented by second-order dynamics. I'm not going to go into details in this video about the mathematics, but I'll show you in the next one. And of course, the movement of the suspended load in the plane, we are going to just consider a plane, is dumped by the air, and of course there is also friction here in this point. Okay. Okay. So what happens if you just plot the position of the in the plane of the suspended ball, considering that this is the initial position, and assuming that we are going to make a movement of it can be 1 meter to the final position. What happens is that we are going to have this oscillatory behavior of the that you can see here. So the suspended load oscillates relative to the final position. That's what we don't want. So if you use this technique, the Posicast, we try to avoid this. So the brilliant idea that Schmidt had, I don't know where he got the idea, but from what I read, it seems that he was fishing, and the movement of throwing the line for fishing, he has a moving, maybe it's a positive cast, and so the movement can be represented in sequential steps, in 3 steps. So first, we have to move the base trolley from the initial position I to an intermediate position H, okay, and stop there. So we have to move from this point to this point and stop here, and then give time so the load, the suspended load, can oscillate from this position, initial position, to the final position. So we have to wait here until this swing is over, and when the load reaches the final position, then okay, move the trolley from the intermediate position to the final position as fast as possible. Okay, and if this is done well, we don't have any oscillation in the final position. So this is a brilliant idea. And of course, in terms of the signal applied to the system, instead of applying a step, because this change of the position is represented by a step, the step here has an amplitude of 1, can be 1 meter. And of course, we have to use 2 steps. The first step, we are going to represent the amplitude by A1, and the second one by A2. And of course, A1 plus A2 is equal to 1. And A2, we have to wait a little bit to apply the second step. Okay, this is the time that you have to wait. I'm going to explain later on in the second video about this time as well. So if it is done that, we apply first A1, which is a part of the step, and then A2, the second part of the step. Then we are going to have a kind of deadbeat response. So this can be represented by a block diagram. This half-cycle Posicast, which was the name given to this control. We got the signal here, and you can see here that we got 2 parts: the A1, the step A1, and step A2. And we can see here that you got a switch here, so the A2 is going only to be applied after this time t, that I'm going to explain later on. So if you add this component, this signal here, with this delay signal here, and apply this summing results in the U, apply to the system results in the Y, and this is what we obtain. You can see here that we get a step from the initial position to the final position, and we got the intermediate position here. In this case, the A1 should be this part. Is more or less A1 is equal to 0.7, more or less, and then we got A2, it is equal to 0.3. Okay, so, and we can see here the result. We don't have this, as you may know, this is called the overshoot. The overshoot here, we don't have overshoot. It's a damped response, deadbeat response, and this is the result that you are going to obtain. Okay, so in terms of the Laplace representation, if you change the signals to Laplace, as you can see here, the operator is S, The difference is that delay is represented by this A with this exponential, where this part here, this td under 2 is the t that is delayed until we apply the second step. Okay, so I'm not going to go to details now, but in the next video I'm going to show you a simulation using Simulink, MATLAB Simulink, and then I'm going to explain a little bit the mathematics. It is not very complicated. So also we can see here the three components. Okay, this is the first step. As you can see here, this is the value more or less 0.7, and we got a part of the response, and then delayed by this time. This is the t, the delay time. We got the second step here, second step, which is more or less 0.3, and we got the result, the deadbeat response. Okay, that is the final response. And of course, adding this signal to that signal, we got this one over there dashed. Okay, so this concludes video 1. I hope that you like it. Thanks for watching.